Hello, my name is R. Sricharan and my roll number is 5D1 and I am from CSC section. Today my topic is tunnel based IPv6 transition. The transition from IPv4 to IPv6 has become an increasingly urgent problem. Researchers have proposed many transition techniques such as network address transition protocol transition or however vendor such as vendor IP ISPs found several serious problems when they tried to deploy these techniques, including rotating scalability, weak performance, and low transparency for upper layer application. Consequently, the internet community had to make some of these technologies and reconsider more particular solutions to the transition problem. We can we can divide transition mechanism into two categories: transition and tunneling. Transition interconnects IP4 only host with IP6 only host by a transition vehicle that converts IP4 packet to IP6 and vice versa. However, However, using transition comes with several challenges. For one thing, it introduces an intermediate element between IP endpoints. Between IP endpoints, thus breaking the end-to-end model. However, the proper transition between IP address families requires IP header rewriting, address and conversion, TCPs and UDP checksum, recomputing, and even application layer transition. A transition vehicle that lacks bandwidth capacity will become a performance bottleneck at high speed. Tunneling Tunneling enables IPv6 connectivity across an IPv4 network and vice versa. Tunneling operating includes encapsulation, decapsulation, and tunnel endpoint signal with no upper layer operation required. Hardware can implement data forwarding at the network layer with line speed capacity, although tunneling can't achieve direct interworking between IPv4 and IPv6. We believe that broadly adopting it as the foundation of IPv6 transition accelerate IPv6 adoption, retain legacy IP4 connectivity, and let operators read their existing IPv4 assets during the transition period. The key concern is that tunneling retains the end-to-end notation and IP like-to-like affinity on which the internet is built. Tunnel-based IPv6 transition framework. Rotation of the internet, including both network in- infrastructures and application service, will remain IPv4 for a long period during the IPv6 transition. From an end user perspective, a network should guarantee both IPv4 and IPv6 reachability regardless of the ISP network IPFL. And for application transparency is mandatory. Different IP protocol stacks as whether one shows in IP and end users are usually dual stack. They own native IPv6 access as well as IPv6 access provided by the tunnel by combining and the end host gets the dual stack reachable ability. Applications running on dual stack capable hosts can employ IPv6 and IPv5 on both. For IPv application, they can communicate it with peers using sessions directly. For applications, they can use VX sessions to interact with tunnels. Dual stack capability application can choose both the IPv6 and IPv stack based on the peers IP protocol. In brief, in single stack network, tunneling can satisfy communication requirements during the transition. Can be tunneling technique used in the internet as much as possible, thus keeping the end-to-end transition in backbone networks. An ISP is likely to run an IPv6 only backbone network during the transition period. Nevertheless, many IPv5 network will be connected to the backbone with tunnel mesh between address family board routers. The backbone can forward IPv6 packets directly. Alternatively, it can encapsulate IPv5 packet into IPv6 on in and decapsulate them on the axis. Ideally, the backbone migration roadmap would be as follows. The tunnel mesh mechanism should not only function in both IPv6 over IPv4 and IPv4 over IPv6 bases, but should also support automatic discovery and combination. IPv5 rotating should be supported between AFPRS to achieve correct forward in IPv5 network and correct encapsulation on AFPRS. Currently, several tunneling mechanisms can fit the backbone scenario, such as manually configure tunnels to 4 IPv6 each, and the software mesh is manually configured tunnel. AFBRS are configured with encapsulation information in a static way. The main drawback is low flexibility and as overwhelming management load for which must frequently perform extensive manually configuration for each tunnel. Conversely, 6 to 4 perform over IPv4 tunneling automatically. Transition in IP4 access network. Currently, most access networks are IP4 only. Nevertheless, network users want to get connected with the IPv6 internet. Therefore, ISPs should provide IPv6 access over IPv4 only network, which connected with IPv6 internet. Therefore, ISPs should provide IPv6 access over IPv4 only network, which they can achieve through IPv6 or IPv4 tunneling. Given that the IPv6 address space inside is much larger than the IPv4 address space, stainless statelessness will be a natural property because IPv6 addresses can be generated by embedding IPv4 address. Transition in new IPv6 accessing network developed in the next few years will mainly be IPv6 only. To provide dual stack access to such networks, we need an IPv4 over IPv6 tunneling mechanism that can sustain IPv4 availability when access network switched to IPv6 and hence significantly advanced the transition. Early tunneling research focused on developing IPv6 over IPv4 techniques. Recently, with the growth of IPv6 access network, the internet community has approved a several series of IPv4 over IPv6 tunneling techniques, including public 4 over 6, dual stack, light, and 4 to satisfy various transition demands. Thank you for giving great opportunity to explain towards in front of you, and thank you.